Empirical formulas, section 3.10. An empirical formula contains the simplest whole number ratio of atoms in a compound. So essentially, if you had something like C6H6, well, that whole number ratio is not 6 to 6, it's 1 to 1, because you divide each of these by 6 and get 1 and 1. So it's a 1 to 1 ratio. The actual chemical formula is different. All that we care about with an empirical formula is we care about that whole number ratio of those elements to one another. Okay, as an example, if you looked at this sort of problem, if you looked at a problem that gave you the masses of a particular substance, or a mass of a sample, you'd have 20 grams of a sample is found to contain 8 grams of carbon, 1.34 grams of hydrogen, and 10.7 grams of oxygen. Everything is accounted for. All 20 grams are accounted for. So that entire substance is made up of only these 3 elements. What you'd be able to do is figure out the moles taking these masses, 8 grams of carbon, and converting it to 0.666 moles of carbon, 1.34 grams of hydrogen, convert that to 1.33 moles of hydrogen, 10.7 grams of oxygen, convert that to 0.669 moles of oxygen. Okay, so what you would get is a formula. You'd get a formula that is C 0.666, H 1.33, and O 0.669. And when you look at those numbers, you'd say, well, that can't be right. Whenever I look at a formula, I need whole numbers. I need C2H4 or something like that, not a fraction or a point or a decimal point. However, what that shows you when you compare these numbers to one another is that you basically have a ratio. And that ratio in this case would be something like, well, for every 1 mole of carbon, there are 2 moles of hydrogen. Because if you took if you looked at 1.33 to 0.66, you'd see that that's a 2 to 1 ratio. So this particular substance has a ratio or molar ratio of 0.666 to 1.33 to 0.669, which whenever you convert those into whole numbers, you figure out that the empirical formula of this substance is CH2O. Identify any empirical formulas and determine the empirical formulas of the others. So for this, what we're looking for is, do any of these have whole numbers, and are those whole numbers something that we can reduce down further? So let's go ahead and tackle B. B shows us that carbon and hydrogen are in a 6 to 6 ratio, which is the same as a 1 to 1 ratio. So our empirical formula is CH. Okay, the rest of these answers are all fractions. They're not whole numbers. So what we can do with them is basically multiply them or compare them to one another and multiply them to come up with whole numbers. So if you looked at this as 1.5 to 1, you could come up with B2O3. Because if you multiplied both of these by 2, both of these subscripts by 2, you would come up with a whole number. Now, if we look at answer option C, or question C, this is a little bit tricky. What this shows us is that there are 2 times as many moles, there are 0.5 to 0.25 moles of sodium to phosphorus. Oxygen, your subscript is 1. Okay, now how would you get 0.25 to be a whole number? You'd multiply it by 4. So we're going to see, well, if we multiplied 0.5 by 4, would that give us a whole number? Yes, it would. If we multiplied 1 by 4, that would also give us a whole number. So we're looking at something like Na2P. P is going to have a subscript of 1, and O is going to have a subscript of 4. Okay. Now, when we relate all these to one another, C3, H 2.67, and O 1.33. When we compare these to one another, well, now we're looking at something where if we multiply this by 3, that's going to bring oxygen to be 1.33 times 3, that would be 4. If we take 2.67 times 3, That's going to give us H 8, and C is going to be 9. So those are all empirical formulas for those. Now, there is a little bit of a guide that you can use to determine what your whole number is going, or what your what factor you want to use. So we noticed that there was one answer, or for our last question we had C3 H 2.67 and O 1.33. Now when you see something like that, what you can do is, these are some of the common numbers that you're going to see, or common decimal places that you're going to see, and therefore the whole number multiplier for those subscripts. So this 0.67 right here, well, anytime you see that, just know, okay, I'm going to have to multiply that by 3, and that will give me a whole number. So we had 2.67, multiply that by 3, and that got us 8. Now, write empirical formulas for compounds consisting of these ratios of A to B. Okay, so what we have to do is look at these numbers and write the empirical formula, AB. Okay, now here for question B, this is a 1 to 1.5 ratio. So we would have something like A2 B3. C, we've got 1 to 1.33. And this kind of alludes back to that previous slide. Anytime that you see that 0.33, you should be thinking, oh, my whole number multiplier is going to be 3, because 0.33 times 3 is 0.99, which basically rounds up. So this would be, you're going to multiply each of these by 3. So A sub 3, B 4. Okay, and then the last one here, 1 to 1.20. So I see this 0.20 and I'm thinking multiply it by 5. So that means A5, B6. Now your steps in determining an empirical formula. What you're going to be given generally is percent data. So you're going to convert that percent data into mass data. And you're going to assume that your sample is 100 grams. Now you convert the mass of each element into moles of each element. Divide moles of all elements by the smaller number of moles. And if you don't see whole numbers, multiply it by an appropriate factor. Insert the numbers as subscripts in the corresponding formula. So this is a good question right here. This is, you have a formula, or you have a compound that is 43.7% P and 56.3% O. Our first step is to convert these percentages into masses, and we're going to assume 100 grams. So I'm going to simply write this as 43.7 grams of phosphorus. And now what I want to do is I want to, after I convert this into grams of oxygen, I want to know my molar mass of these different things. So using my periodic table as a reference, I know that oxygen has a mass of 16 grams. Phosphorus has a mass of 30.97 grams. Of phosphorus is 1 mole of phosphorus. 16 grams of oxygen is 1 mole of oxygen. I want to convert my masses into moles. So now I get my calculator out and I say 43.7 divided by 30.97. That gives me 1.4 moles of phosphorus. Okay, now my next question is 56.3 divided by 16. That gets me 3.5 moles of oxygen. So effectively what I've come up with is I have come up with the formula that is P 1.4 to O 3.5. Dandy. Well, kind of. but also a problem. It's a problem because, well, I can't really work with those formulas, or I can't really work with that as a formula. So what I need to do is I need to take the smaller number of moles and divide it by each one to figure out my molar ratio of phosphorus to phosphorus and phosphorus to oxygen. So I'm going to say 3.51 divided by 1.41. That's going to give me an answer of P1O 2.5. Okay, so what I did was I determined the number of moles of phosphorus and of oxygen. Then I related them to one another. Okay, so the first step alone, simply figuring out the number of moles, that's great and that's essential, but you can't figure out an empirical formula until you relate the two substances to one another. Now, whenever I see this as my molar ratio, P1O 2.5, well, this is something that I'm going to multiply by 2, because if I multiply 2.5 by 2, I get a whole number of 5. I'm also, as a result, going to have to multiply that 1 by 2. So I'm going to end up with P2O5. And there you go. There is a perfect example of a percentage-based empirical formula calculation. I hope this was helpful, and we will proceed onward.